Problem number 14. Determine convergence or divergence of the series, the sum of n from 3 to infinity of n squared minus n minus 1 divided by n cubed plus 2n plus 1. So when I see this series, the first thing that catches my mind are the terms being added and subtracted in the numerator and denominator. So these are going to be red herrings. They aren't going to affect things in the long run. As n gets bigger and bigger and bigger, n squared is going to dominate n and 1. N cubed is going to dominate 2n and 1. So as n gets bigger and bigger and bigger, this fraction gets closer and closer to n squared divided by n cubed. So at this point, I already know I'm going to use a comparison test. I'm going to be comparing the series whose terms are n squared minus n minus 1 divided by n cubed plus 2n plus 1. I'm going to be comparing the series whose terms are this fraction with the series whose terms are this fraction, n squared divided by n cubed, which simplifies to 1 over n. Now, at this point, I should say I'm going to use a comparison test. I don't know yet whether I'm going to use direct comparison test or limit comparison test. Direct comparison test is going to be easier for us to use, but direct comparison test might not apply. So we'll just continue to chase things out, get things set up before we decide which one of those two comparison tests we're going to use. Okay, so we're going to compare the behavior of this series with the behavior of this series, the sum from n from 3 to infinity of 1 over n. And so this is a truncated harmonic series, truncated in the sense of we lost the first couple terms. That's not going to change behavior. We know the harmonic series diverges. It's a p series where n is equal to 1. So at this point, I basically know that this series is also going to diverge. That these terms shouldn't affect the behavior of the series. So by discarding them, I get a series that diverges. So this original series also should diverge. Now I have to fill in the details to get there. I'm going to try direct comparison test. And if that doesn't work, I know the limit comparison test is going to work. The limit comparison test will have just a little bit more work to it. Okay, so for direct comparison test, I have to figure out which one of these two fractions is bigger. Well, this one the one on the left has a smaller numerator than the one on the right, and it has a larger denominator than the one on the right. So both of that is making this one smaller than this one. So I can conclude that this fraction is smaller than this fraction. Okay, so is this in the right direction or is it in the wrong direction for us to use the direct comparison test? So unfortunately, this is in the wrong direction. That this shows that this series up here is smaller than a series that diverges, but this series might still diverge or it might converge. So just because you're smaller than a series that diverges, that doesn't tell you one way or another whether you converge or diverge. If the inequality had been in the opposite direction, if this was bigger than this, then we could say this series is bigger than the series that diverges, and that would be enough to say that diverges, but unfortunately, we can't use the direct comparison test here. Okay, so we can't use the direct comparison test. What can we do? We'll have to use the limit comparison test, and we'll call this a sub n, and we'll call this, b sub n. Okay, so we want to calculate for the limit comparison test. We want to calculate out the limit as n goes to infinity of a sub n, that's n squared minus n minus 1, divided by n cubed plus 2n plus 1. All of that divided by b sub n. I'll just write the 1 over n version here. So to evaluate this limit, I'm going to, instead of dividing by 1 over n, that's the same thing as multiplying by n in the numerator. So that would give us n cubed minus n squared minus n divided by n cubed plus 2n plus 1. Okay, so at this point we have this limit here that we want to evaluate. It's not too hard to see that this limit is 1. a couple of different ways we could do it. We could change everything to x's, apply L'Hopital's rule several times. We get 1. Maybe an easier way to see this is that the numerator and denominator are both polynomials of degree 3. And so the limit as n goes to infinity is simply going to be the ratio of those of the respective coefficients there of the leading term. So it will be 1 divided by 1 is 1. Okay, so the limit, this is the limit as n goes to infinity of a sub n divided by b sub n. What does the limit comparison test tell us here? Well, I'm zeroing in on the important part of the limit comparison test. If a(n) and b(n) are positive sequences, and if the limit as n goes to infinity of a sub n divided by b sub n is equal to L, then if L is if this limit exists and is something strictly positive but not infinity, then the series that's the sum of the an and the series of the bn's, they have the same behavior. That means they both converge or they both diverge. So there's nothing magical here about getting 1. 1 is an important number in, say, the ratio test or the root test. You look to see if your ratio, the limit of the ratio is less than 1 or greater than 1. Here, this 1 doesn't mean anything other than it's a number that is positive. It's not 0, but it's not infinity. So that tells us that these two series are going to have the same behavior. And so because we know that this series diverges, so that finally tells us that this series also diverges by the limit comparison test with this harmonic series where the first couple of terms dropped. Okay, let me recap. We see these terms here that are kind of irrelevant. We drop them. So we know we're going to do a comparison test with this series, which we know that this series diverges. So we know that this series is going to diverge. We just have to prove that. The direction the inequality is in the wrong direction for the direct comparison test to work. So we use the limit comparison test. We get 1, which is something between 0 and infinity. So sure enough, these series have the same behavior. So because this diverges as well.